Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mail, and I'll be helping moderate today's webinar, Performance Benchmarking in Julia. In this webinar, we'll look at some of the tools for tuning your code to get the most out of Julia. We'll examine some of the report tools, such as @profile and SnoopCompile.jl, how we define some impactful optimization thresholds in Core.Inference, and show you how to tune up Julia for maximum performance. You'll be shortening runtimes and compile times with precision in no time. We'll also discuss how some of your plans for future improvements, some of our plans for future improvements, and the ways we track and eliminate regressions with each release so you can feel confident in upgrading versions regularly. We'd like to have this session as interactive as possible today, so please write your questions in the chat and we'll either address them on the fly or address each question individually following the demonstration. With that said, it's my pleasure to introduce today's presenter for our performance benchmarking in Julia, Jameson Nash. Jameson is a software engineer at Julia Computing and a Julia language contributor working on the compiler integration, language design, and performance tooling. Jameson?
Thanks, Eric. We've got lots of tools here that I'm excited to show you. This is what I do on a day-to-day basis, basically, is just trying to find which tool can figure out why something's not working as it should. So I'm hoping to give you those tools today, too. The most straightforward one I find is Profile. It's built into Julia, so it's always available. It's been available since a fairly early release of Julia. I want to say like 0.1 or 0.2, although it's gained a lot of new features along the way. And so it lets us dig in and say, I've got this whole application. I don't want to have to change anything yet, but I want to know where it's going to be useful to explore deeper. So for example, if we want to look at a fib function, we're just going to simply compute the Fibonacci sequence. We're going to do it pretty inefficiently, but we're going to do it in a way that will let us then start to dig in and see what ways can we make this better. So for example, here I've got two different functions. One is just simply calling into the other one. I've marked them both at no inline so that they'll actually both show up and I'll get the stack I want. And then the straightforward definition of fib is that if the n we're looking at is greater than 1, we call fib recursively on the previous value and the second previous value. We add those together, and then we have a base case. If n is less than 1, we just set them all to 1. Then we can see here, if we just simply time fib on, say, 40, it takes about 0.8 seconds, and that's hopefully the value of fib at that point. Then from there, we can go ahead and profile it. We've already compiled it. We've made sure that it's ready to run, and we're not going to include some extraneous bits in our benchmark when we want to actually just look at the performance of fib itself. That can be very important. So then we call the @profile function and give it some code to run. And once I did that, I got back a performance profile, which I printed out. I gave it some arguments here. I wanted to just list out what the functions were. So I said flat, and I wanted to sort it by count. So count is the ratio of time that was spent in there. We're roughly taking a profile snapshot every millisecond, so that's roughly 555 milliseconds, but there's some overhead, there's some system noise, and so it won't come out exactly the same, which we can kind of see because it should have come out to about 806 and we only came out to 555. But there's some strangeness here. One thing that we see, well, it's not a strange thing, but one thing we see is that all of the fib numbers here are just forming this very tall stack. It's very repetitive, and then it forms a rather fun-looking shape. I think it gives you a good sense of how the fib algorithm computes and crunches all the numbers and recurses, but it can be kind of hard to see where the analysis is. And then we've got some oddity here, and if you look in that corner, you'll notice a large fraction of this says that we just called less than directly from the REPL. Why would we do that? That doesn't seem to make sense. And so if we look in total here, there's quite a few snapshots total. And so if we look closely, they would actually add up. But there's just some weird noise here. So can we do better? And it turns out there is some ways to do better. And so one thing we can do is turn off a particular optimization pass that makes it hard for profilers to do their job. And so that particular one currently requires a code change and a recompile. It's a very small change. We just remove some if-defs in the codegen file. And it's this option called FPO, or frame pointer optimization. Without the frame pointer, it has a little bit harder time walking through the stack. With it, now suddenly our stack doesn't have those missing ones. They can see they ended up here where they should have been. This stack is also using a separate option that I added about a year ago called recur, and it takes a keyword argument. In this case, I passed flat. And so this took all the recursion that we had and flattened it down. So instead of showing that very large tree, we just see that fib called fib_r, and we know that it was repeating some number of times. And then eventually we see a couple different calls here because each call site of fib shows up as a different point in this stack. And because there's two call sites, when we look back here, we have fib_r twice. So that shows up as fib_r being twice in our profile. And so I think this helps break down profiling results in a manageable way in a lot of cases. This can be really helpful, for example, when I'm trying to profile Core.Compiler, which is this large tree of functions, and then it recurses. And so every time you go up, it starts at an entry point, and then it walks through the code and eventually gets to a new call, and then starts over with that call as the base, and we work back up through the stack. And so by flattening it, we can potentially see more closely what percentage of the time was actually being consumed in fib itself, and what percentage of the time was being consumed in some of the integer operations that fib was doing. I think this is a very helpful way, and if you want to learn more about this particular trick, I have a blog post that goes into a few more details about this and other profilers that you may encounter or want to use. They all show roughly the same thing, but they can have different trade-offs, or they're just designed for different languages, and we can compare and contrast some of the features. It's not the only profiler out there, as I said. There's actually more in Julia itself, and so I'm going to walk through a couple of these and pull up an interactive view for some of these. So let's see. I want to. There we go. The first one I'll pull up here is profile SVG through and profile view and Visual Studio Code. So all three of these are mostly presenting the same interface, but loaded from a different portion of the ecosystem. So if we have Visual Studio Code here, this is Visual Studio Code, and I've added the Julia language support. I've got Julia Hub, and I've got a flame graph visualizer that we'll get into later installed that lets me run code. Where is it? Execute file in REPL. And what I've created here is a very short script. It's just going to pre-populate a REPL environment for me with a bunch of things that I don't want to have to type. Why isn't that coming up? Can't see. Demo. So this provides me with a number of different tools, and among those I've loaded profile, and I've got profile view loaded here. And in this environment, there's actually already a built-in system. So we can go ahead and profile fib again. I think I need to define fib first. So as I showed before, we can time fib. That took a little longer than expected. the right definition of fib? It seems okay. But since it was slower than expected, this may be interesting to see what we get when we profile this. Previously we saw this take 0.8 seconds. So we can go back through, like seeing this often just to get a sense if the whole profile looks about right, if the top of it is about right. Oh, I've got some old things in my profile, so let's clear that and start over. I think something's confused and stuck. I think I've noticed one of the, I think I filed an issue about it. One of the profiling packages, when I start the user interface for it, blocks certain signals. And so it blocks the profiler, which is very inconvenient. And and kind of forces us to start over when we want to Okay, that's looking better as well. So I think there was some interaction going with one of the packages I had loaded. There we go. There's the fib that we had before. And so with this tool, we can actually then open a visual editor. So we can go ahead and view that profile directly. And oh, that got very squished. And this gives us a number of tools to dig into it, so we can see the total time and then start to work down through. We can also click this flame graph button. And as I mentioned, I've installed a flame graph option plugin to Visual Studio Code. And this allows us to see where exactly all the time was being spent. This gives us two views. The first view here is time. So we're seeing as the call stacks grow and shrink very quickly, each of those forms a snapshot of what fib was doing. This isn't a precise call stack, so it didn't make precisely this number of passes up and down the stack, but it had this overall shape. We got how does one make key presses appear as tooltips? Oh, that's an application I'm running, Keycaster. So as you'll see, my keystrokes are showing up so that if I hit anything weird, you'll be able to see it on screen, what buttons I pressed. Then one of the other buttons you want to know about in this view is this one, which then gives us back to our other view. So it aggregated all of those tall, skinny stacks and gave us back one thick one. So instead of showing time in seconds across here, it shows duration. And this is often a much more useful graph because you can see if events happen periodically, it aggregates them all so you can see them much closer together. So great tool to see. There's some others like it. pprof is a project out of Go that has a wrapper in Julia, does something similar, but has a few different ways to look at it. And then, as we said, profile.jl is built in. There's a number of options to it that are great for trying to dig into your problem and find out what's going on and what's significant. We already saw the format options. With flat, it gave me a table. The default is tree, which draws somewhat of a flame graph, but rotated sideways. And I can go ahead and draw that now as well, if I can find where I hid my REPL. Possibly closed it. Let's just rerun. Hope that comes up. This again will show us a number of different ways to view the information. And I think it's helpful to see because it'll I think, help explain some of the other options when we see those. Someone know how to make this reappear? Show terminal. Aha. Kill terminal. Okay. So we can do the same thing, but we can pass no options and we'll get a tall stack here. So very similar to what we saw before, just rotated on its side. Some of the other useful options can be whether or not you want to show C frames. Most of the time, C frames are internal to Julia. And so by hiding those, we effectively end up hiding a lot of the internal infrastructure for Julia, which can help make the profiles a little bit quicker and easier to read. We have options for how you want to care about code. So there's a combine option that combines all instructions that are on the same line of code, even if they are different instructions, and you can turn that off so you can see each instruction separately. I find one of the more useful ways to actually use this is instead of applying the combine option, if I have a particular piece of code that I have identified as being some portion of my time and that is interesting, I'll split it out into a bunch of different lines of code so that each operation, sub-operation it does has its own line number. And then I have fine control over whether it appears in the same line of the profile or a separate line of the profile. And that I find can really help me dig down and see which part of the profile is more important. We can apply some other options to try to limit the size of the tree. Max depth is sometimes useful if you just have this tree that's getting away from you and filling the whole screen. Sorted by doesn't apply to the tree view, but when we were in the flat view, I showed I was sorting by counts. It can also sort by file and line number. It's a very common one, or you can sort by overhead. So there's two different ways you can look at the performance measurements. And if you look here, there's two different numbers. So we have first 116 here and 117 here. And what these two numbers mean is the amount of time spent exactly on that line, and later the amount of time spent somewhere in a call with that line. So for example, this 2 means of the profile, 2 of those samples happened in eval. 252 happened because of a call of eval. So we have an overhead of 2, even though we have 252 of our samples there. And that can be very useful to see the difference between those two. Noise floor I find is a really fun one to see. I don't know of any other language that has this currently, or other tool. This allows you to limit frames as a percentage of their parent frame. And so we've looked at the definition of what noise is and figured it's kind of usually when you're looking at statistical noise, there's usually this square root factor. So if you're familiar with Bernoulli probabilities, we take the square root of p times q over n, or some with some constants in there, I believe. So when we look at the noise floor, we multiply it by square root of n, where n was the number of samples of the parent. We can try to get an estimate of how much does this caller affect the parent, and then we can try to show only those subcalls that actually had an impact on their parent. Similarly, sometimes it just helps to put a min count threshold. So if we have 1,000 samples, we don't really care about the ones that only were 1 or 2. And so we might set a min count of, say, 10 or maybe 10% of our total. When noise flow, I find 1 works really well, or if there's too many samples, maybe 10, but usually 1 I find just works quite surprisingly well in most cases to cut out a significant percentage of the profile without it removing any of the useful information from it. And finally, the recur option I showed can be very useful. So flat takes any call to the same function at the same line and treats it, in my head, I think of it as, treats it as if you had turned that into an iteration. It's a common idea that any recursion could be re-expressed as iteration, and any iteration could be, or most iteration, I think any iteration, can be expressed as recursion. They might have very different characteristics. It might be difficult to make that transformation, and it might often be quite useless. So it can be helpful, I think, to have a tool that may give you a view as if it was converted to iteration. And so thereby combining a bunch of things from all over the place that were separated in our profile and put them on the same level so that we get a lot shorter profile and we can see a little bit more, okay, every time this function called this other function, how much time did that take, regardless of how deep in the call stack that happened. It's a bit of a hybrid between the view from flat, which removes any information of where it's called from, and the tree view, which requires exactly the same stack for showing how much cost each child had. Once you have some idea, or in other cases where you have an idea but you want to see it differently, it can be really helpful instead to use TimerOutputs. TimerOutputs gives us a similar view on the result, but we need to do some manual annotation. So in this case, where we have knowledge of something very specific, we might want to specifically say that we're going to care about one particular region of the code. We don't want to see the entire code. We know kind of what's going on, but we want to see what operations now take the most time, and we might want to add some particular information to it. So we can redefine our fib function, we can redefine our fib r function, and so all I've done here, as I highlighted in the slide, is add @timeIt with the to argument and gave them both names of some sort. This has a lot higher overhead, so I can't do fib of 40 anymore. I found I can go up to about fib of 30 now has about the same cost as fib of 40 had. And finally, I need to define our timer output object. And now when we run fib of some number, as I said, it takes a lot longer, but we get this much more detailed information. It can tell us time very precisely. It can actually tell us the number of calls, which is something we couldn't have found out from the profile before. There we have the number of occurrences, so it was time-based, but we didn't have the number of calls. We just couldn't derive that information by that method. And this also provides us with allocation information, which we could potentially add to the profile view. We have not done that currently. And again, shows this high nesting level because we are looking at something very nested. And so TimerOutputs has a flatten call, which will let us combine all of those into a much more compact table and see where our time is being spent. Because we're just alternating back and forth, we can see the time and the calls are the same or within a small ratio of each other, because there should be about the same number of each. So quick recap, profile is a great way to find the places to optimize. They won't tell you how to optimize, but it's a great place to start. It's not the only place to start. We can also go back to the basics. The simplest thing we can do is just to time it. That's generally what we care about. How long did this take? How long am I going to be waiting? what we call the time to first plot problem. We've even got an acronym, TTFP, is something we track very closely and is often a benchmark I'm using probably forever now. We're going to just put the time macro in front and see how long it goes. And this has gotten upgraded in 1.6. So now we used to have allocations and GC time. It now will also show compilation time. So we can see what was each of the different pieces that were contributing to making that time very slow. Or we can even go more verbosely. So there's a time V. These are run in separate REPL sessions, because if I had just run them sequentially, this second one would have been very fast. But instead we show about the same amount of time. And so we can see precisely how much time was elapsed, what was in doing, how much did we allocate, where did we allocate them, and just get a full detail about just the wall clock time of this operation. And I think this compilation time is LVM time. I'm surprised it's quite that low. I was expecting higher because we know the plot itself only takes a fraction of a second. So this isn't showing us fully where all of our time is going. But that's not my goal today, to look precisely into that. We'll figure that out. That's something I'll keep working on offline, is trying to figure out how to get this number just a lot smaller. And I think we have a number of ideas for how to do that on the back end. The goal is really, we call it time to first plot, but the goal is really just latency for anything. We don't want to do something that only affects the latency of plots. If there was something that only affected that latency, we would probably do it if it wasn't affecting anything else negatively. But we really want to find ways that everything gets benefited. And so once we find those out, we want to take the next step. So we've done all this manual work, and so now we need to automate it. And there can be a lot of gotchas with things. There can be a lot of gotchas with things like at time, because it is timing exactly the operation you give it, but it might not be quite exactly the one that you thought it would be. And so there's little things you have to sometimes be aware of, like the fact that at time we'll start compiling this, and some of it may have been compiled before. So to get a very accurate measure, we may need to specify that we want to see the time after compilation or before compilation. So we might rerun some portions of our code early and then rerun time to see what happens after compilation. We might do the reverse. Staking. There it goes. So one thing that can be useful to do is actually add a val after this, because that will add essentially an inference barrier. We could add a more direct inference barrier. I can show some of those as well, and try to cover some of what inference barriers there are a little bit later in the talk. And so, well, I've given it a slightly different command here as well. Plot doesn't actually pop up the plot. It returns a plot object. And then the second thing it does when it returns to the REPL, it defines a display object, and that will take the rest of the time. So this took a little bit longer because now we're including a little bit less of the compilation time. And you can see this is very high in compilation time. So we really are interested in finding ways to drive that number down without sacrificing runtime performance. And it's always a very hard trade-off, that if we're just generating one plot, it's kind of annoying to wait 14 seconds for it. But if we generate the next plot, it's now 800, well, we'll call it a millisecond. So if we're generating thousands of plots, this can save us quite a bit of time in the end. And I wonder where the plot went. Oh, there it is.
Jameson, real
It
quick.
gave us a nice little plot. Mm-hmm.
Hi, Jameson. Real quick,
Yeah.
someone asked you. You'd mentioned inference barrier. Rick was just wondering if you could define that for us, please.
Okay. Yeah, I want to talk about that later, but I'll give at least a quick overview of that. So one of the things that I'm especially benchmarking is this compilation time number, which is something I'm hoping to talk a little bit about later, is how you can also improve that number. Um, and what that time is time spent inferring, optimizing, and compiling the code. And so there's a few different tricks you can put in, usually barriers, that tell the compiler to stop here. Don't look past this. Don't try to look beyond this point. And so if it's going wild and it's spending a lot of time trying to analyze and come up with the best answer for some piece of code, but you happen to know that it's not going to come up with a great answer. It's going to come up with an answer, but it's going to take it 5 seconds and it's not going to be useful. We can put an inference barrier in to tell it this is acceptable. We don't need this information. Don't bother spending time looking for it. And by running the profiles, we can try to see where those points that start complex inference graphs look like. And that's something I'm going to get into in a minute here. But first, a separate tangent in a different direction. When we're timing things, as I said, there's things you have to look into, such as how much compilation was going on, and do we want to put in inference barriers in different points in time. And so there's a package called benchmark tools that helps you automate some of this. One of the classic ones is btime, which is designed to have the same interface as time, but runs the code you give it as a benchmark. Instead of running it once, it will run it enough times to figure out how that code actually performs in an application. So let me go ahead and load this benchmark tools. Oh yeah, it can be fun to see how many methods are in some of these. I think MapMole is the winner, especially after loading some packages. I think I've seen thousands of methods for it. If you are ever looking for ways in which Julia is very far extended, it is definitely in the mathematical realm where there's so many different combinations of possibilities. But okay, so let's btime fib, I need to redefine fib first. So we're going to take out our timeit macros and we run those two. And then we can at btime fib instead. And so let's wrap that in at time as well. So what you'll see is it takes a lot longer, first off. When we ran at time initially for fib 20, I think it finished in about a millisecond. And here it's working a lot harder. It took 13 seconds and it came back and told us fib 20 takes 52 microseconds. And so by contrast, we could have done this manually, but our numbers can be all over the place. We got 59, we got 64, we got 79, and then which one is it? btime, because it's run it many more times and it's tried to eliminate some common factors that can drastically impact our total time, it can be much more useful to see this number from btime. You can see it spent a bunch of time doing GC for us, which was not part of the benchmark. It just wanted to make sure that we didn't get some side effects because I've been typing things in my REPL all this time. And some of that could have been building up GC pressure. And then we run our benchmark and, oh, now it's saying it's going to take all this GC time or compilation time doing things that weren't actually related to the benchmark at all. And so this has a bunch of other options as well. This, for the most part, just tells me to look at benchmark, which is what we're going to do next. When we look at the help for btime, it says there's actually a number of other parameters. Time doesn't have these parameters, but btime does. And because it's running things multiple times, we might give it, say, a setup command. So we'll say we initially want to set a number I, and then instead of calling fib, we could call fib of I. There's teardown options. So we could print that number, say. We can also give it the number of iterations. I think is n iters. We can give it, I believe, max time and min times in seconds. Don't want to take that long. Okay, how many did I mistype? Okay, it's not n iters, it's evals. And it is just seconds, which is a good name for it. Much more descriptive. So then we tell it we only want it to take 2 seconds and then tear down, print it out, or tear down a bunch of times. So the second one to look at here is at benchmark. And at benchmark takes exactly the same arguments as btime. Yes, it is. And its main difference is it's going to give us a more exhaustive report. And so it's actually returned an object of type benchmark tools trial. And so we could query this object and find out what was the least number of memory or the first number of memory allocations, what was our minimum, medium, maximum time, how many samples did it decide to run, and how many evals per sample. So because we know this runs fast, we actually might realize, oh, this actually needs a lot more evals. And we could set the number of samples, but that's usually not necessary. And so if we set the number of evals to be something higher, we may get a slightly more accurate number or just reduce the time variation here. And this gives us even the ability to see every single run, how long did it take. So we ran 42 trials with 100 evals each. Each of those then gives us exactly that time. And we can save this to disk. And as we get through all these steps, at some point it gets to realize, well, okay, now we're repeating a lot of this. Maybe I should make a script of this. Well, now we have at benchmarkable. At benchmarkable, instead of running the benchmark, says, I want to declare that there is a benchmark. And I want to declare that it is fib. And then I can run that later instead of running it right away. And so that is, in fact, what we do. As I said, the theme is automation. So we need more automation. And whenever we commit something to base that looks like it might have a performance impact, or some roughly daily, I've been spawning it manually. I need to set up a cron job and do my automation. We can look at how has performance changed over time. We especially look into this for every release to say, let's make sure for the things that we've known in the past are performance critical, we haven't run into a regression. We spent time in the past to say, here's our profile, here's what matters. Then we spent time to say, how much time was it taking? How do we write a benchmark to make sure we're getting the fastest performance we can? We wrote a script, and now we can put that onto a server and run those. So the server here is this nano soldier. That link was supposed to open somewhere. There it is. It's Keynote is preventing me from opening it. Open link. It is open. It is just not letting me put it on the correct screen. Okay. And this is something we've set up for base Julia to make sure that there's no regressions. And we can directly call this from the command line, from PR. So for example, open that one. At various points in time, we will run this, and we have a bot. So we just go on the command line, we tell NanoSoldier, just run all the benchmarks. And we've got a AWS server configured. Oh yeah, that's what I want to look up. So we've got a provisioning script here. As I said, automation is important. And so there's lots of little things that can affect benchmark times. This is currently running on an AWS machine, so there's some things that affect time that we can't control. It used to run on a bare metal machine that gave us a little bit more control, and it was improving our benchmark times a little bit. But there's a bunch of different little things you can do that we put together here on how to get a machine that's very quiet. These are documented in the benchmark tools repository as well. So if you're interested in setting something up for yourself or running on CI, this may be a useful script for you. What that then does is after it runs that, it comes back eventually and says, hey, I've got a report for you. Here's what's happened recently. And so for each of those things that we've defined as being at benchmarkable, it comes back and says, okay, relative to the last time I ran that, this benchmark ran 7% slower. And so we expect some amount of noise. Sometimes the benchmarks themselves are not written in a way that's quite stable enough. So there's some variation in the benchmark itself. Sometimes it's just noise on the machine. Some times the frequency of the machine might not be quite as stable. Looks like unless we pay Amazon a lot of money, they won't let us disable the frequency scaling on the machine. So we expect some amount of noise as it frequency scales up and down as the workload changes. Which means memory ratio usually is a very important one. If that goes up or down, then we know, oh, we actually changed something, and we should probably look into that. Often, otherwise, it's just the fact that we're running thousands of tests, and so some percentage of that will fail statistically over time. And then the other thing to note, though, is that as I showed here, we can change the number of, oops, gotta find the right window. As I showed here, we can change the number of evals per sample. We can also ask it to try to guess a good number for that. And so it says 1. So there's some heuristics in here. The author of this wrote a paper on how do you try to determine how many evals is worth doing per sample. And so you give it in some parameters, like I think it should take about a second, and it'll come back and say, okay, actually, you need about this many evals per sample to try to get good timing. And then after we've timed that, we can run it, or we could save that tuning to a file and run it later. And so in this case, what it has one of those files saved, and then we load that file in so that every time we rerun the benchmarks, it gets some of the similar parameters so that we get comparable results, and it helps try to cut down on the noise that we might otherwise get in that plot. And all of these are located in this base benchmarks repository. And we've got a whole range of things. Sometimes they are contributed. So there's a fairly old system called Shootout that has a bunch of just random problems. We've got some micro problems that are just really tiny benchmarks of different things. We try to benchmark our parallel. We've got sparse arrays. So there's a whole bunch of things in here, and we're always looking for new things. So if you have a benchmark that is very important to you, but it doesn't require custom code, but it is something that you know how to describe, we can add that here. And then for each release, we'll track that and make sure it doesn't get slower so that when we release a new version, it performs as well or hopefully better than the last version of Julia. That is very specific to Julia. It said base benchmarks. Fortunately, the community has created a repository called package benchmark, which has a similar concept, but is targeted at packages. And so, for example, we can look at one here in TKF's repository. And so he has installed benchmark CI on benchmark CI. And so there's a bot here, and it just runs on GitHub Actions. There's no particular special environment needed. The more you can control the environment, often the lower noise you can get, which means you can see slightly smaller variations. But oftentimes the regressions we're looking at are like 2x or 10,000x, and those are relatively easy to see even in a noisy environment. We can say, oh, 10,000x isn't noise. That never happens by noise. 2x, occasionally that's noise. With a relatively fast benchmark, it can be relatively easy to see it take too much time on just one run and it skew the whole thing. So only a few people I've seen use this so far, but I think it's really great that that's available. Because like CI is so important that we have for every commit to find out, did we break something? Sometimes performance can be equally important. And for base Julia, it's been really important when we merge major changes that try to, say, change an inlining threshold or change an optimization threshold. We go to this to say, what will this affect? Will we break something that we weren't expecting in a performance sense? And most PRs don't break something, so we don't have to run it on every PR. But that peace of mind, knowing that we can run it, has really helped allow us to fix a lot of performance regressions and avoid adding new ones. Let's see, I have about 10 minutes left, so I will try to leave about 5 minutes for questions and talk about some of the optimizations that we can do. Up till now, we've mostly talked about performance of runtime, but there's ways in which compile time can either be more important or sometimes it can be the same thing. If you spend too much time compiling, sometimes you end up just generating too much code. And now what should have been an optimal algorithm has too many copies of that algorithm, and then it spends too much time figuring out which was the fastest algorithm to run over actually running the algorithm. And so over time, we've developed increasingly fine-grained ways that you can try to tell the compiler, this is important and this isn't. And so one of the ones that's still experimental, although I think it's relatively stable, is an opt level. And so for something like plots, where we know there isn't any really small tight loops that need to be vectorized and really carefully taken care of, we don't want to just run the whole thing in the interpreter. That is still fairly slow. But we can set this opt level and we can set it to a number. So we can say opt level 0, meaning don't do anything beyond the very basic level optimizations, all the way up to opt level 3. Default is typically 2. You can set this on the command line also, so you can run Julia with a -O flag for optimization level, and we can tell it 2 or 1, or we could just say 0. And we can see correspondingly what times go up and down. We could, for example, look at our @fib function again and see if that's changed at all. And for the most part, right, it hasn't changed at all. We're going to get a little bit slower. So we're at about 800 milliseconds before. Now it's taking 900 milliseconds. So not optimizing. It is costing us a little bit of runtime. But, and I didn't measure compiling time, so I don't have that specifically to show how much it saved. If we add an add eval here, now this will capture the time. How does, we'll get to that in a second. So that took us, well, only 1% compilation times. But if we ran with default parameters, we can rerun that whole thing. Okay, so compilation costs us a bit, 0.136% instead of 0.172. Very small overall. And you can see it actually paid for itself. So running the slower compiler, it actually took longer end to end than running the compiler and then running the benchmark. There's other ways you can optimize in a more specific way. So no specialized can be a very useful one. And so how you use that is when you're defining a method that takes very general parameters. So often this is types, or it's something that sees everything in the system. I have an example of this. So when we look at this, typically, actually, I think it's in this window. Actually, with running out of time on everything here, I'll say this is a place where you can look up the SnoopCompile repository, and I want to talk about SnoopCompile a little bit more, but I'm just not going to have the time. So SnoopCompile is a tool that lets us see where time was being spent in the compiler specifically, and it lets us then try to pre-compile those outputs and see where we could potentially spend less time and improve our metrics. So we can analyze different methods. That should have been defined here. And so we can define code, say, in a module if we have a double wheel and we're looking at how it's defined. We can ask SnoopCompile to give us those method instances and what to do with those. If we've defined some code that is just very inefficient at how it's running, so for example here, one of the examples in the SnoopCompile repo is spell type, and it calls spell type on type T, where T. And when we do that, if we say grab a bunch of types, say all subtypes of any, and then try to call spell type on every type, we're going to incur a lot of compilation because every single, we've told it with this where T that every call to this should be compiled separately. And so this can take a very long time. And so then what we can do instead is write no specialize. And tell it we don't want to specialize on T because we've seen this just will take a long time, 33 seconds. And the second time would have been fast, but right, 0.003 seconds, but we're not going to save that amount of time. And so we want to, we'll call this spell type 1, and we load this in the REPL. I think it's running. Okay. So now when we redo that, but we use spell type 1, oh, that's missing a character. And then I'm gonna hit Control Enter, which will send that over to my REPL and rerun it. And now you can see it took 0.06 seconds. So there was no compilation needed. We've never run this function before, but much, much faster. So no specialized can be a great trick to know. That this is a form of a compilation barrier. There's other ones. There's literally base.inference barrier, which says, don't look at this value. There's base.invoke latest, which says, don't look at this function call when you call it. And so there's lots of little tricks like that that you can use. And there's even some inside base, such as we've got this any16 inside. So it says for tuples up to length 16, do one algorithm, probably fully unroll it. But when you get too long, fully unrolling an algorithm starts to get really expensive and really slow, especially to compile. And so we want to be able to switch algorithms. And so we'll switch it currently now it's actually any32. So we switch the algorithm once you have 32 elements. We want to switch usually to an iterative algorithm. So that's SnoopCompile. Very quickly as an overview, I won't touch on Cthulhu, another very useful tool, so I'll just give it a shout out. If you're looking then to get further into understanding where things are and what they're doing, this is a very useful interactive code utility. Once you know what you want to look for, to try to see what the function is doing. It gives you a very low-level view, but it can be a very useful view if something is taking more or less time than you think that it should. And as it's about 1 o'clock, I will pause for questions. I'll stay on longer if anyone wants to ask questions later as well. You can also find me on Slack often. I recommend pinging in public Slack channels because often you may try to ping me, but someone will actually see the question and answer it before I can get to it. And it just benefits anyone else who wants to see similar questions. I see one question here on setting up the NanoSoldier bot. For that, I recommend looking at the nanosoldier.jl repo itself on GitHub. So I can paste that link here. So it's not just on my screen. That has some information on how to set up the repository. It is very tightly coupled to base. So I will in some ways warn you that it may not be directly useful for you. At some point, I think we probably should try to find ways to merge package benchmark and NanoSoldier, where package benchmark is the one that is a little bit more configured to run other people's code, where NanoSoldier is very specifically configured right now to run the base benchmarks repository. But I don't think it would be terribly hard to go through and remove the code that's, say, building custom versions of Julia and just set it up to grab custom versions of your package instead and generate those reports for you. I don't have any particular advice on benchmarking linear algebra operations. No, I usually defer those to others of my colleagues that are more knowledgeable about linear algebra. Any other questions?
If there are no other questions, we are a minute past the hour. Certainly appreciate everybody for joining us here today. You can reach out to Jameson, as he mentioned, on Slack. Otherwise, feel free to use the discourse channel to reach out to us and learn more about the Julia community and the Julia language. Thank you so much, Jameson, for your time and the excellent presentation today. For the recorded version of this presentation and our past webinars, you can visit the resources tab at juliacomputing.com. For any help with your existing Julia use case or upcoming Julia project, please feel free to reach out to us at sales@juliacomputing.com, and we'd be more than happy to help. Thanks again, everyone. Have a great day. Have a great Friday and a great weekend. Take care.